just by the size of the audience, I can tell that, this is an overhyped research area that I work in. Let me try to gather some few quick statistics from you guys. So, this is the Department of Physics, so I assume that all of you are physicists, but like who tinkered with machine learning and AI before? Raise your hand. Wow, okay, that's like a third of the audience. How many of you specialize in quantum physics? Oh, that's awesome, about like 25% of the audience. You don't need any quantum physics to understand quantum machine learning. Which is good because then, the remaining 75% of the audience can also understand it. So what I really want to talk about today is, first of all, what this field is about and why it is mainly interesting to physicists and not so much to computer scientists. There seems to be a disconnect. And it's strange because when I talk about this topic to a physicist, the physicist will tell me that, this is computer science. But if you talk about this topic to a computer scientist, computer scientists, they will tell that, this is too much physics. I refuse to understand it. And I'm kind of stuck. So I'm a faculty in the University of Toronto, but the physics department, the doors are closed, then with the CS department. So somehow I ended up being an assistant professor in the Rotman School of Management. It was a puzzle to me. Okay, so I really don't want to talk about AI and machine learning so much. I just want to give you this very intuitive picture of it, which is actually by a physicist, by Max Tegmark, who published this really good book a year ago. So Max Tegmark is responsible for making AI safety research mainstream. So he was the first person who considered the safety of future artificial intelligence seriously. And for many years, he tried to get grants to get this research funded, and now he is the main figure of this line of research. And he has this really nice metaphor that AI is like a rising tide, and it's taking over different tasks that were previously reserved for human cognition. So, it already nailed chess a good 20 years ago, then it nailed Go a few years ago, and eventually if you take over driving. I'm looking forward to that day because I hate driving. And eventually it will get to theorem proving, and eventually it gets to the point of designing itself. And some people say that at that point there's going to be this explosion of intelligence. We'll reach a point of singularity in human evolution. And but what I want to point out really is that this rising tide takes a lot of effort from us. And machine learning and artificial intelligence have a history going back about 60 years. And there were many waves of rapid advances, and then the whole field just collapsed because people were over-promising what would be possible by an advanced AI and then not delivering on those promises. And we are witnessing this cycle again. So right now we are living in this era of deep learning. And deep learning made fantastic advances in image recognition and captioning images and segmenting images into different semantic parts. And it also made fantastic advances in machine translation. And we can mention a few more areas, but that's about it. So that's what deep learning is capable of. For instance, it's not capable of formal reasoning. So if we want to move forward and we want to do theorem verification or theorem proving with AI, then deep learning is not going to get us there. And so some people in the machine learning community say that a third AI winter is coming once deep learning sizzles out, and there will be again no funding. And now you can say that you just throw quantum resources at this problem and you just accelerate AI research. And that was the idea of quantum machine learning. So quantum machine learning actually has a surprisingly long history. The first paper I consider quantum machine learning was published in 1994, but the field really took off 5 years ago when Seth Lloyd and a couple of his collaborators published 3 papers over the summer, and they were offering exponential speedup in certain machine learning algorithms, and there's a reason why I put machine learning in air quotes. But anyway, so that really attracted a lot of researchers. to the field. But almost exclusively, these researchers were physicists. So this is like a brief timeline of how many papers were published on quantum machine learning. Well, not published, but this is the appearance on arXiv. So in 2014, straight away, there was this explosion, 25 papers immediately, just like 6 months after the summer of 2013. And 2015, 2016, 2017, like it's been advancing. Okay, it's not an exponential rise, but still, you see, it's a fair number of papers every year. I had a very scientific way of calculating how many papers were published. I was just looking at my folder of to read and sorted by year. But the strange fact is that all of these papers are by physicists. So if you look at where these papers were published, only 2 or 3 of them were published in actual machine learning outlets. The rest were published in physics journals. Initially in PRL and Nature Physics and whatnot, and later it went down the impact factor line, and then you end up with quantum info and computing. I got into this field right in the beginning. So I started thinking about quantum machine learning in 2012, but at that point I was focusing on a very different problem. I was focusing on machine learning and supercomputers, and then when I read these 3 papers by Seth Lloyd 5 years ago, I was like, this makes no sense from a machine learning perspective. Like, you are offering me an exponential advantage in algorithms that, first of all, I'm not interested in anymore, because they accelerated algorithms that were used in the mid-1990s in the machine learning community. And second, they twisted these algorithms and to fit the quantum protocol that they wanted to apply to get this exponential advantage. But by twisting them, you lost the main component why these algorithms were interesting in the first place. So I got very angry about it. I started blogging about it, that these papers make no sense. And then a publisher contacted me that, hey, these blogs are really good. Do you want to write a book? And that's how I ended up writing the first book on quantum machine learning. It was born out of anger. But it made no difference, right? Because you see that there's just 2 or 3 papers in machine learning outlets. It's because these papers are mainly irrelevant to the machine learning community. And what is the cause of this? So first of all, machine learning people are quite happy without knowing any quantum physics. They have just so many interesting problems to focus on, and many of them are applied projects. And if you end up working for a company, your salary is just completely outrageous. So machine learning people are perfectly happy without bothering about quantum enhanced machine learning. And then the big annual gathering of machine learning people, and especially deep learning people, is a conference called NIPS. And NIPS is a very big conference by any standard. So it has about 5,000–6,000 visitors, hundreds of talks, parallel sessions, anything that you can imagine. And it runs for 6 full days. And just to tell you, that scale alone, is not comparable to a quantum machine learning workshop where 20 people show up. And these are the same 20 people who showed up for the previous quantum machine learning workshop. But what's interesting about this year's NIPS, which is going to be in Montreal, is that it's sold out in 11 minutes. That again tells you about just how happy machine learning people are without knowing any quantum physics. And the last part is what I really want to talk about. That vast majority of QML research is just focuses on the wrong questions, which are irrelevant to machine learning people. And basically, my research tries to address the right questions, what I hope to be the right questions. And I hope to convince you to also put your attention on these questions if you want to jump into this, which leads me to my next question. So you see that there have been 60, 70 publications a year on quantum machine learning, and sort of the low-hanging fruits are gone, right? And now if you want to contribute something that is meaningful and that's going to be published in some high-ranking journal and it will make a difference to the world, then you have to work hard. And so the question is there a quantum AI winter coming? And I have a very simple answer to that. It's no. And well, the reason it is because, first of all, I need to get tenure at some point, and so this research has to go on. And then, I get papers rejected very often that, hey, this paper should go to a more specialized research. And guess what? We got our more specialized journal. So we are launching a journal on quantum machine intelligence. So the field is definitely not dying. But these are not the reasons why the field is actually not dying. The reason this is not dying is because there are more and more companies producing quantum computers. And what's interesting about this landscape of commercial quantum computing is that, okay, so they get funding to build a quantum computer, whether it's superconducting, trapped ions, or whatever it is, but they don't really know what to do with it. Because these are noisy, imperfect, they suffer from all sorts of problems, so they're not very good for these quantum algorithms that have been developed over the last 20, 22 years. So the question is, they have just small number of qubits, and you can put a few gates, and that's all you can do with them. And then what's a good application area for them? And it turns out to be that quantum machine learning, at least a small part of quantum machine learning, is very well suited for this early hardware that these companies are actually trying to build. And eventually, I think that it really goes two ways. So on one hand, quantum computers can give you a lift in certain classes of machine learning algorithms. And on the other hand, you can incorporate machine learning at any point in the quantum technology stack. Whether it's a quantum compiler, whether it's the actual control on the chip for some superconducting circuit, you can add machine learning at many, many different places in this pipeline and make quantum computers more scalable, more robust to noise, or more adaptable to noise. So it goes back and forth. With better quantum computers, you get better machine learning algorithms, and the other way around. With better machine learning, you can get more scalable quantum computers. And I very quickly want to go through the major paradigms of quantum computing, because if you're not in this field, it can be very confusing from the outside. Because when we talk about quantum computing, we are talking about actually very different paradigms. And the first one, and this is the easiest to explain to computer scientists, is just the generalization of your digital computer. So in a classical digital computer, you have bit strings, and you use logical operations to transform these bit strings. In a quantum computer, what you have is a probability distribution over bit strings, a quantum state, and you are applying gate sequences to transform this probability distribution, this quantum state, into a new one until it is expressive of the problem that you are interested in. And you have to be very, very careful, because governments really wanted to build this model in the 1990s. It was because of this algorithm that you see here. It's Shor's algorithm. It would allow you to factor a number exponentially faster than what's classically possible. And governments wanted this because then they would be able to crack encryption. But if you just run a quick calculation, the encryption schemes that we use today that are vulnerable to an attack by a quantum computer use 1024 bits, which means that you need at least that many qubits to express the problem on a quantum computer. And the number of gates that are required to implement this algorithm scales at least quadratically with the number of your qubits, which means that you need at least 1 million gates, to implement this algorithm. Now, if you look at what we have, we are going to see some results are created. So we have, say, 8 or 16 qubits, and you can put maximum 12 gates on those qubits to perform an operation and still get meaningful results. So there's a big gap between 12 gates and 1 million. So we are very far from being able to actually realize this model. So that's paradigm one. Paradigm 1.5 is the same thing, but using continuous variables. So instead of qubits, you have Q-modes, and this is a more physicsy way of thinking. You have quadrature operators, Gaussian states, Fock space, and that's the probability distribution that you are trying to massage into a shape that you want it to. Then the second paradigm is quantum annealing. Here you use the adiabatic theorem to achieve a calculation. This is the hardest to explain to say, computer scientists, because you actually have to have some understanding of the adiabatic theorem. But the idea is that you have some simple Hamiltonians, say, containing only on-site transverse fields. You find the ground state of that particular system, and then you slowly tweak your Hamiltonian into something that you're actually interested in, for instance, a classical Ising model. And then if you do this transition slowly enough, that is, you obey speed limit, then you stay in the ground state. And then you can just read out that ground state, and that gives you a solution to essentially a quadratic optimization problem. And the key here is this slow enough, because calculating how slow you have to go in this transition is actually harder than solving the original problem. And when it comes to implementations, you just ignore speed limits and you anneal many, many times, and then you take your solution with the lowest energy as the ground state. But there's no guarantee whether you actually read out the ground state. And then the third paradigm is what Richard Feynman originally envisioned as this is what quantum computing should be about, which is about quantum simulators. So say you are interested in some large quantum antibody system, then you would need a supercomputer that just doesn't exist to do non-trivial calculations on that system, because the size of the Hilbert space grows so fast. So he said that, hey, let's build a smaller quantum system, which we can control, and simulate the larger quantum system that we are interested in. And so these quantum simulators are somewhat conceptually simpler, because you don't require universality in the calculations. So there are a couple of built all around the world. I'm not aware of any commercial enterprise building one, but academic labs definitely build one. And I have a tip for you how to avoid research directions that don't yield anything relevant. If you see that the European Union puts money into it, just stay away from it. They launched this quantum flagship program, which is €1 billion this year, and like half of it goes on boson sampling, which is a kind of quantum simulator. So you can be 100% sure that quantum boson sampling is just meaningless. It's a form of showing quantum supremacy for the sake of quantum supremacy, but it doesn't really have any applications. Okay, so why quantum enhanced machine learning? So the main thing here is that contemporary machine learning already uses a variety of different hardware. So you started from just central processing units, and then about 10 years ago, GPUs appeared on the machine learning scene. GPUs, graphics processing units, have been around for 20 years. But about 10 years ago, they became useful for the kind of calculations that you perform in machine learning, and in particular in neural networks. And that's what really enabled deep learning. That's why we had this revolution in deep learning, and that's why there are just so many billions of dollars poured into deep learning research today. GPUs consume a lot of energy. So the pipeline is moving down to FPGAs, which are programmable gate arrays, so you can actually set the circuit from software. So you can perform very similar operations, but at a much lower cost. And at the very end of the scale are these application-specific integrated circuits, which implement nothing but a specific neural network, for instance, but they consume very low power. So these are now being integrated into phones to recognize your face, and also you can buy this USB stick just running some neural network. And then the question is like, what else you can throw into this mix? And I really think that this is where contemporary quantum computers start to come into play, because everything in this mix so far focuses on the kind of things that are good for deep learning, which is, and deep learning is very good at supervised learning. It's very good at discriminating things. It's very good at discriminating between cats and dogs. It's very good at deterministic operations. So if you ask a neural network twice about the same image of the cat, it will say cat twice, or dog twice if it's not very accurate. And they are very easy to parallelize. That's why they were enabled by these graphic processing units, because you can just parallelize thousands of calculations at the same time. So leave everything that belongs to this category to classical hardware, because we can already solve it efficiently. So there is no point in throwing a $50 million quantum computer at it. But there are tasks which remain difficult for classical computers. And these are unsupervised problems where there are just no labels to begin with. For instance, you want to identify some characteristic in a large network, in some large social network. And it's very difficult, it remains very difficult to do generative models. So it's very easy for a deep learning network to tell whether an image contains a cat or a dog. But if you ask it, hey, generate me an image of a chihuahua, that's very difficult. So that's a generative problem. And it's very difficult to make probabilistic statements, like rigorous probabilistic statements about the quality of your predictions. And stuff that's not parallelizable. And you are restricted to serial calculations, but then they remain very slow. So that's, again, not meaningful. So those are the kind of learning algorithms that you should be outsourcing to a quantum processing unit. And basically, the rest of the talk is about going through what you can do in these kind of problems. And I have a warning for you. This was the teaser image for this talk. So 10 years ago, well, even 6 years ago, I was working on machine learning algorithms for supercomputers. But I was absolutely not interested in deep learning. When I first heard about it, I was like, this is the stupidest thing. And I never thought it would work. So what I was focusing on was shallow algorithms. And there was this algorithm called the self-organizing map, which is a kind of a shallow neural network architecture. And I poured all my effort into parallelizing it and running it on supercomputers. And this is what a self-organizing map looks like. So it's able to do this unsupervised kind of learning that's typically reserved for, but it remains a hard problem. And years went by, and I was still working on my self-organizing maps. And today my papers are cited 12 times, whereas any deep learning paper is cited 12 times an hour. So I kind of missed the train. And quantum machine learning risks the same problem. So if you focus on problems in machine learning that are not interesting to people, or you can solve it better with classical resources, just don't do it. Just focus on the right questions. Find your questions first. So let's go through these application areas. So the first one and the most obvious one is optimization, right? So when you think about quantum annealing, it's just finding the ground state of a classicalizing model. And contemporary implementations do not implement this nearest neighborizing model, which would be the most intuitive. They have this funny looking graph. And in the next iteration of the chip, it's going to look even funnier. So your task as somebody developing a quantum machine learning algorithm using this architecture would be mapping the problem that you have in mind into first of all, to a quadratic unconstrained binary optimization. And then once you have that, it has certain connectivity structure. And then you have to embed the connectivity structure in the hardware. That's really the question. And then you keep your fingers crossed that you get the ground state at the end of it. But that's not your only option. So what's appealing about quantum annealing is that you already have 2048 qubits, and which is a large number, but it has a sparse connectivity, and there are all sorts of problems going on. And but you can also use a gate model quantum computer, so you have much fewer qubits. So the largest that you can access for free has 16 qubits. There are a few others that you can access for free. Alibaba has 11 qubits. Rigetti has 8 qubits at the moment, but that will very soon change. And then you can run something called QAOA, Quantum Approximate Optimization Algorithm. This is a funny idea, and it goes back to 2013. Until 2013, every single quantum algorithm that was developed had this holy grail in mind. This beautiful, infinitely scalable, noise-tolerant, robust quantum computer that we are never going to have. And this quantum computer is always 20 years away. It's like fusion power. So I think we are going to have fusion power, fault-tolerant quantum computers, and artificial general intelligence on the same day, 20 years from now. And in 2013, there was this algorithm coming out, which was called variational quantum eigensolver. And what was special about this algorithm is that it said, hey, the quantum computers that we're going to have over the next decade or even longer will have a limited number of gates that you can put on them. They will have a limited number of qubits. So what can we use them for? Can we develop an algorithm that would give us some advantage over classical resources, given all the limitations? And they answered in the affirmative. So variational quantum eigensolvers were the first example. And the quantum approximate optimization algorithm uses this algorithm as internally to do an optimization essentially in an Ising model. So it also gets you the ground state of an Ising model. So again, your duty as somebody thinking about a quantum machine learning problem is to express that problem as an Ising model, and then you can run either quantum annealing or QAOA on it. But then the question is, what do you use discrete optimization for in machine learning? Because when you think about, say, a neural network, it's also about optimization. You have some training data coming in, but eventually what it boils down to is a first-order gradient descent. It's a stochastic gradient descent. It's the stupidest thing that you can do. And that's why it's annoying that deep learning works. It's just conceptually too simple. And you could say that, hey, I just take my deep learning network, put it on a quantum computer, and train it faster. And here's the problem. So on a classical computer, say in a graphics processing unit, you represent one weight in this neural network that connects two neurons by a 32-bit precision floating point number. The reason you represent it by a 32-bit precision number is because it's a graphics processing unit which was developed to put pixels on your screen, which have 3 channels, right? That will be 24 bits, and they just padded it with another byte because that's a nice unit, and that's why you are restricted to 32 bits of precision. But that's good enough precision for neural networks, and so that's 32 bits, right? And you can use 16 qubits in total on IBM, and you can use a total of 2048 qubits on the DWF quantum annealer. So you can only put like a handful of weights on any of these quantum computers. And on a realistic neural network, you have billions of weights. So there's no way that you can optimize a deep learning network on a quantum computer. It's a complete misfit. So you have to think problems that are intrinsically discrete, right? Ideally binary. And so there are such problems in machine learning. So one very good example is this method called Ensemble Learning, where you have different machine learning models. So you have a very large neural network, and you have a different neural network. You might have some third architecture, which is not even a neural network. And they want to predict the same thing. And to reduce the uncertainty in the prediction, you average over, you combine their predictions to get a more accurate and a more accurate predictor. And but combining them in a non-trivial way is still an open question. So this is called Ensemble Learning, and since you have a finite number of models, it's naturally a discrete problem, and it works very well on a quantum computer. So the very first quantum machine learning demonstration, which was way ahead of its time in 2008, was doing this. And then exactly 1 year ago, this idea was revisited. And what's interesting was that they throw an ensemble method trained on a quantum computer on finding the Higgs boson. And that's an interesting problem because the Higgs boson was found by very deep neural networks. The neural networks did the filtering. They threw away a lot of information, so you would be able to focus on the decay process that was actually interesting. But since it's a deep learning network with billions of weights, it's not explainable what it is that it throws away and what it is that it keeps. So you don't get any insight on the underlying physical process. And what's interesting in an ensemble method is that it's quintessentially shallow. It just combines different models. So it's easier to explain what it outputs. And that's why it was, I think, a very interesting result, that you can train an ensemble method using a quantum computer that is more explainable than the original discovery of the Higgs boson, and you get some physics insight on what exactly going on in a decay process. Okay, so that was one big application area of quantum machine learning, optimization, and what you have to think about the right problems in machine learning. The second one is sampling. When you think about a quantum state, that the most natural thing to do in it is to measure it and get some classical information out of it. And in a different language, this means that you're sampling a probability distribution. And when you think about sampling on using on a classical computer, then it's very difficult to do in general because you would have to use Markov chain Monte Carlo methods. So you would have to prove that your Markov chain will eventually go to some stationary distribution. Then you would have to think about how long it takes for your Markov chain to burn in, so you can actually start pulling out samples of your distribution. These are expensive things to do on a classical computer, whereas it's a very natural thing to do in a quantum state. Just keep measuring it and you pull out samples. And that's actually what you do at the end of the day when you, for instance, focus on quantum annealing. Because as I told you, if you use this paradigm and you obey speed limits that you cannot possibly calculate, then you have some theoretical guarantee of staying in the ground state. But that's not what you do, because you anneal 1,000 times and then you throw away 999 samples and you keep the one with the lowest energy. Well, what's interesting is that if you keep all 1,000 samples and you plot them, they follow a specific distribution. They follow a Gibbs distribution. And actually, when you think about the physics of it, it's not so surprising. So you have this chip, which is cooled down to 50 millikelvin, which is cold enough, but it's not that cold. And it interacts with the environment. So it's not a closed quantum system. You want it to be a closed quantum system, but it's not. It's an open quantum system. So actually, it thermalizes while you are annealing. In fact, if you can slow down annealing, it will fully thermalize with its environment. So, and if you pull out samples from a thermal state, then of course you get a Gibbs distribution. So it's a very natural correspondence. So at this point, you no longer treat the open quantum system as your enemy. You no longer look at this thermalization as something to ignore or get rid of. You use it as a resource to generate an interesting distribution for you. And what is it interesting for? It's interesting for training an entire family of machine learning algorithms that we simply don't use because classically they are difficult to train. A very good example is Boltzmann Machines. So the training of Boltzmann Machines requires you to pull out samples from an equilibrium distribution of a Gibbs distribution. And classically, you would not do Monte Carlo chains for this because they're too expensive. So to use them at all for any purpose, you truncate your Markov chain after the first one or two iterations, which is just horribly inaccurate. So you can use it for some niche problems, but they are not in the mainstream of machine learning simply because you can't train them efficiently on classical hardware. On the other hand, if you can pull out samples from a thermal state in 50 milliseconds, then training suddenly becomes feasible. So, and Boltzmann machines also have this sparse connectivity structure, and that's a very good fit for the sparse connectivity structure between the physical spins implemented on a quantum annealer. So it's a very, very natural fit between the two. Let's not talk about whether it works in practice. It does not, but it should. So Boltzmann machines belong to a much larger family of machine learning models, which are called probabilistic graphical models. And what unifies these models is that all of them require pulling out samples from some distribution. And like half of this family requires you to pull out samples from a Gibbs distribution. So as long as you can find some subfamily within these models which is the kind of sparse connectivity that is going to be there for years to come on quantum computers, you are looking at something interesting. So here's one of the examples we tried, and it sort of worked. This is a very curious model. So I told you that in the beginning when I showed you this image about the rising tide, that deep learning is not going to give you formal reasoning at all. So if you want to go towards theorem proving and that sort of stuff, you need to incorporate logic. And like logic is sort of a bad word when you talk to a deep learning researcher, right? They just don't like this. But when you trace back the history of artificial intelligence, there were many waves of this more formal logical reasoning took over for short periods of time. So this is what we call today good old-fashioned AI. So this is first-order logic and higher-order logic applied to specific domains. But the problem with first-order logic, it's very rigid, right? So it cannot deal with uncertainty. It cannot deal with probabilities. And when you have real data, when you confront the real world, like everything is probabilistic. So if you encode that, if there are clouds in the sky, then there's going to be rain, then this statement will never, or it will very seldom correspond to reality. And that would be like a first-order logic statement. And if you combine these models with uncertainty, that's when you get really powerful models where you combine logical reasoning with uncertainty. And so there is this other family of models which are halfway between probabilistic graphical models and good old-fashioned AI, which is called statistical relational learning, and that does just this. So it allows you to go back and forth between the two models. But again, you don't use them because they are just very expensive to use. They're very expensive to train, and they are very expensive to use even after you train them on like neural networks, which are sort of expensive to train, but they are manageable. But once you train them, they are very cheap to use. So the example we gave was on Markov logic networks, which take a large collection of first-order logic statements, and they generate an undirected graph based on that first-order knowledge database. And the good thing about it is that the way you generate the Markov network has this sparsity structure that we are looking for. So it also very naturally maps to the kind of quantum hardware that we have today. So I think this would be a good example of quantum machine learning, which brings something to the table to AI researchers. Okay, so the first two examples that I mentioned were such that you started with classical data and you ended with classical data, and you did something quantum in the middle. And so the last area I want to go through is different. So here you start with a quantum state and you end with a quantum state. And this is more natural to a physicist, I think. So I think the most important question that you can ask in this scenario is how you generalize all these rich results that we have in statistical learning theory to the quantum setting. What are the fundamental limits of learning? Like, what is it that a qubit can learn from its environment, for instance? Or how do you define these various probabilistic guarantees that the high-level theory of statistical learning tells you? And there are just a few papers on that. And these are very interesting questions. Hard questions, like mathematically hard, but I think they are very relevant to physics. You can say new physics by looking at older models using this kind of framework. It's like more learning theory type framework. And then the second one is to claim this exponential speedup, which always remains elusive. So this is the kind of algorithm that, say, Seth Lloyd and his colleagues were talking about. And the core idea here is they usually go back to the same algorithmic primitive, which is quantum matrix inversion, which can be done exponentially faster, except that you need more particles than you have in the universe to invert a matrix. But let's not go there. So where do you get quantum data from? It's a very silly thing to think that you can just prepare classical data on a quantum state. You do your quantum protocol, and then you do state tomography. because then all your exponential advantage goes away on the state preparation and the tomography part of the algorithm. So don't do that. This is always the question I get. So somehow these crackpots always find me. So hey, can we use a quantum computer to mine Bitcoin? So I used to say just no, do something better with your time. But recently I became a bit more evil, and I point them to a paper which is really difficult to read and makes no sense. But anyway. And the second example which is a more natural source of quantum states, is this last paradigm of quantum computing I talked about, so quantum simulators. And then, the internal workings of a quantum computer are quantum states intrinsically. So these are good sources of data for any quantum learning algorithm. But I want to show you just how bad it is today. So for years, I tried to implement this quantum matrix inversion protocol, but it's a very, very tricky protocol. And if you read the original paper, which came out exactly 10 years ago, it's really funny because it actually does not do the inversion. So it extracts eigenvalues, and it says that, hey, if you have these eigenvalues in this whatever superposition and you do a controlled rotation, then you can do the inversion of the eigenvalues, and based on that, you get your matrix inverse. But they don't tell you what this controlled rotation is. And that alone is a very deep circuit when you start working out how you would do that inversion. But anyway, so it's a long story, but the point is that we finally implemented it. And we ran it on 2 actual quantum computers. First, we tested different noise models, and we saw that you throw more noise at it, then of course it's not going to give you the inverse matrix. And then we threw it at the 2 quantum computers that we could access at that time. One was the 16-qubit IBM quantum computer, and the other one was an 8-qubit superconducting quantum computer from Rigetti. And I told you that you can put around 10, 15 gates on these qubits, and then they go to hell. And it shows here because this circuit had 12 gates as we defined it, but then the hardware couldn't implement all of those gates, and there were some connectivity issues, so we had to reshuffle some qubits. And so you ended up with a circuit between 15 to 20 gates, depending on whether it was IBM or Rigetti. Rigetti needed more gates because it had more limited topology. And on IBM, we got a fidelity. So this is probability of success, but you can translate that to fidelity, like how much overlap you have with the state that you actually want to get. And if you translate it to fidelity with IBM, you get around 76%, which is so-so. I mean, that was better than we expected, but it's still completely useless. And then we ran it on Rigetti, and we got probability 1/2 of success. And if you translate that to fidelity, that's 0. 0 overlap with just a handful of gates on a toy example of inverting a 2x2 matrix. That's how bad it is. So that's your exponential advantage. Be very careful with these exponential algorithms. And what's really funny about this, that IBM was so happy with this result that we are in this top 5 winning teams of ever developing something on the IBM quantum computer. They were like, yeah, this is what we want. And Rigetti is also very happy with the 0% fidelity. So they asked us to write up a blog post on it, like how fantastic this result is. So they are certainly very enthusiastic. Anyway, so what I want to close with is that actually, like much of quantum machine learning research and application happens right here in Toronto. So if you are interested in this field, then you couldn't be in a better place. First of all, the authors of the first 2 books on quantum machine learning work here. I happen to be one of them. And the other is by Maria Schuld, she published the 2nd book on the subject a month ago. And she works for this quantum hardware startup here called Xanadu. So first of all, you have just a quantum computer factory down the road, which also helps. They're building this CV type of quantum computers. And I'm the academic director of the quantum program in the Creative Destruction Lab, where we take in 25 startups a year who focus on some application of quantum machine learning, and they try to build a business around it. And we partner with a bunch of hardware providers, and there's funding and mentoring, so it's a really fun program. And then the U of T finally made some really smart hiring decision. They hired me. And then they hired Henry Nguyen in the CS department. He gives the first ever quantum computing course in the University of Toronto. And Alan Asper-Guzik, who is a quantum chemist, moved his entire group from Harvard to here. And he brings in a lot of this quantum machine learning mentality. So fantastic things are happening here. And just a few more words on this accelerator program. It's not an accelerator program. It's an incubator program, really. So the way it works is that we do a recruitment worldwide. We try to bring in people from like all sorts of backgrounds, like machine learning, quantum physics, quantum computing, at various different levels. So master's students who are just finishing their program, fresh PhDs, but also more senior postdocs. And we give them a training in quantum machine learning, like quantum computing, machine learning, and quantum machine learning. And we give them business guidance, we give them technical support, and we link them up with 3 hardware providers, which is D-Wave, Xanadu, and Rigetti. And they get some seed money that gets them going for about a year, which is the duration of the program. And they have a chance to just test different ideas and see whether there is actual value in using these quantum resources in the short term. So if you are interested, we will start recruiting for the next cohort soon, but by soon I mean in about 5 months. These are the hardware partners. And if you are interested in more, there are lots of things happening. So next Tuesday, I'm going to give another talk on a more specific result. So I'm going to explain how we ended up with that comparison between IBM and Rigetti and zero fidelity. I will explain the whole paper and how it led to that experimental results. So that's going to be Zero Gravity Labs on Richmond Street, apparently. And then we are trying to educate the machine learning community in quantum computing, trying to convert them one by one. So we're on a lecture series in the Vector Institute, and every second Thursday, the next one will be on next Thursday. You are also welcome to attend. And then we will have a half-day quantum computing and quantum machine learning workshop in December in Rotman. Details will go online in a few months, but you can just email me if you want to come, and I keep you posted. And I'm putting together the very first massively open online course on quantum machine learning, and the planned launch date is February next year, and I need beta testers. And by that I mean I develop course material, and I need to run it on people to see whether it actually works. So if you are interested in testing material for this course, again, just email me. You can download these slides themselves. I put them on my website. And we brought up a 12-minute introduction to quantum machine learning with Maria Schuld. That's also online. And we might have some open positions for PhDs and master's positions reasonably soonish, like again, a few months. Hopefully not more than that. So that's it. I finish here. My time is just up. I leave the take-home message here, and I'm happy to take questions. Thank you.